Welcome to God Talk Improv, a show where a rocket scientist and a medical doctor, who is also my pastor, talk about current topics in science and faith, all in 15 minutes. So let's get started. Dr. Andy, welcome to the show, and please give us a topic.
Yeah, Doug, today we have a very interesting and relevant topic for improv. We're going to talk about the Hartle-Hawking theory of cosmogony. Now, what that means in
Yes,
human
please.
terms is we're going to discuss relevant theories out there by theoretical physicists and other cosmologists who try to describe what happened right after the initial inflation of the Big Bang singularity. So we're basically talking about cosmogony means how things began, how the universe began. That's what the study of cosmogony is. Cosmology is the study of the entire cosmos, but cosmogony talks about the theoretical ideas and philosophies and mathematical models that try to predict the initiation and the beginning of our universe. So we're going to talk about those theories today, and specifically this Hartle-Hawking theory involves imaginary numbers, imaginary time, and a lot of mathematical gymnastics, I think, to try to get around explaining the fact that the universe has a beginning, and anything that begins to exist has to have a cause. And if it has to have a cause, it has to be outside of space-time, which implies God. So I think they want to try to get around that beginning and say there was no partition, right?
Right.
So that's what we're going to
first,
talk about.
Tell us what in the world this Hartle-Hawking is.
Well, let's talk about it. If I like to explain it like this. If you have I want you to imagine one of those orange cones that would be sitting in the road as you're driving down the highway and they're blocking off the left lane, okay?
Right.
You know how those cones look, or an ice cream cone. If I pulled that up, and I'm talking about a cone that goes to a point, mathematically, as an engineer, you'd be able to describe to me that if I started at the point and went out, and both of those were lines on the edges, they would go out away from each other into infinity, right? And they would never meet.
Right.
And you could draw a calculus equation that as you moved closer to that, if you went backwards and started out and went backwards towards that point, they would be going at certain rates until they got there, right?
Correct.
Okay, when we would do that, let's think of the universe that way, that it's a cone. If it's shaped like a cone, as the universe is expanding, let's imagine taking those two legs of that cone and moving back through time until we reach that point where there's a infinitely dense mass of a matter that would be the singularity, which at that point, that would be as far back as we could go to describe the beginning of the universe. Now, let's say that we go back behind that a little bit, or before that.
Right.
We got a partition here between space-time and nothing. So before that singularity, if we go back to the beginning before that, there wouldn't be anything. There would be nothing. So once that comes into existence and then begins to inflate and expand, we have the Big Bang. Well, Hawking doesn't like the theoretical ideas, the philosophical ideas, I should say, or theological implications of such a model as a cone. If it's a cone, then in fact it does have a space-time partition, or a beginning, and if we got a beginning, we got to have a cause for something to begin to exist. So to get around that, Hartle and Hawking have a mathematical model that describes something that looks different than a cone, so that the beginning of the universe doesn't look like a cone going back to a point and nothing, but he describes it as looking like a badminton.
A badminton, okay.
What do you call the not a tennis ball, but a badminton that you would hit?
Right.
Now, if you notice the way they look, they're kind of cone-shaped, and then they come down, and then they're rounded at the bottom.
Right.
So he says that's the way the beginning of the universe was. It never came to a point. It came down and has a rounded bottom. And if that's the way it was, there really was never a beginning. It was just there. It was just sort of a quantum vacuum or some kind of matter that existed in that base of that. It didn't come to a point, because if it comes to a point, you've got that partition. He's trying to get away from the partition and say it wasn't shaped like that.
Right.
Now, apparently he's not arguing for steady state universe, and I don't know if he's arguing for a universe that expands and contracts. I don't know. But he's describing the shape of the universe different to get away from that point so that he doesn't have to deal with the philosophical implications of our universe coming from nothing.
Well, there was another reason, and that is because in both general relativity and quantum mechanics, they break down at the earliest moments of the Big Bang.
There you go.
But that's because quantum mechanics do not permit particles to inhabit a space that is smaller than their wavelength.
Right.
So
there's a difference. So let's make sure we talk about that.
Yeah, you're getting so condensed,
so small,
so dense
that the mathematical laws of Newtonian physics break down.
Correct.
And they go into quantum. But he's saying that you can't bridge those two mathematically, so we don't know how to do that because of gravity, I guess. But can't bridge those two. So is that also why they're trying to use this model?
They're trying to do something to get away from that. You're coming from a very small point. I mean,
right? Oh, infinitely dense mass.
If it keeps on going, right? You're coming to a point. It's going to
infinitely dense.
It's At one time we talked about a number on here, the density being 1 billion times 500,000.
Right.
Grams per cubic centimeter.
Right.
And the whole universe will occupy a sphere that went out halfway to the moon, right?
Yeah.
If it was just right here, it'd be all the way out halfway.
Right.
And that was 1 nanosecond after the Big Bang.
Okay.
Well, now you're going to crunch that down more and more and more.
To something infinitely small, like the top of a pin?
Yes.
And even smaller.
That was 1 nanosecond. So
that was 1 nanosecond. So let's go to 5. I don't know.
0.1
nanosecond. Whatever.
Yeah, it's going to have to get much smaller, right?
So let's just keep pushing back, and eventually we're going to become to that infinite density. Now, before that, we assumed that it didn't exist at all, that there was nothing, and then it came into existence.
That's correct.
Now, what happened before that? Is there any way, as a physicist, to know what, or even to know what it looked like? Did it look like a badminton, or did it look like a cone?
Well,
we don't know, do we?
Let me give you some comments on that. All right.
What are imaginary numbers? We got to get to that.
All right. Let me give you a couple comments. First, this is from Robert Nuremoff, who is assistant professor of physics at Michigan Technology University.
Okay.
He says, first of all, it is not really known whether or not the universe started from a singularity. Our measurements cannot take us back only so far. Ideas about the nature of the cosmos at the start of the Big Bang are mostly unproven conjecture.
Okay.
So
what's that say to you?
That tells me that you can only go back so far, and after that, if you try to go back closer than 1 nanosecond, even at 1 nanosecond, it's crazy. But if you try to go back before that, then you're just guessing.
You're guessing.
It's a belief.
It's a belief. Okay, so if you're telling me that any of these theories that try to describe what things look like at 0.1 nanosecond or
even that or
0.0005 nanoseconds, whatever, we're getting even at 1 nanosecond. You say the space would all the universe would be from here to halfway to the moon. You said
1 nanosecond.
Okay, so that's that's at 1 nanosecond, and even at that point of the Big Bang, we really are.
You're guessing.
Conjecture. It's conjecture. So if we're talking about going back further, how do we know? Okay, so we're guessing. So that sounds a lot like faith to me. It doesn't sound so much like science. I mean, we don't really know.
Let me tell you what these guys are doing. These jokers. All right, this is the astrophysicists such as Krauss that we've had a lecture about.
Right.
This is Hawking. They're using equations to predict many different things, even micro black holes.
Okay.
And that doesn't mean they exist.
Right.
The equations can predict
the equations predict it.
But it doesn't,
doesn't mean they exist.
And they're trying to take recent measurements from satellites that precisely measure the cosmological background radiation.
Okay, the cosmic background radiation is what they're looking at.
Right.
Okay.
And it's now they get very precise measurements on them, right?
Okay.
So let me tell you what they're doing with that is let's go to analogy. It would be the Trinity site.
Okay, now, for this, are you going to explain why they have imaginary time and imaginary numbers? And just so people understand,
All right.
They have to use imaginary time. This is not, I'm not saying what you're going to explain, but from my standpoint, they have to have imaginary time because they're talking about, Hawking says, in the very beginning, there was space, but there was no time. That's what he says.
Right.
Okay, so he says, usually we have space-time. You know, if you got space, you got time. If you got time, you got space. He says it broke down to a point where in the very beginning, you've got that dense place where you have space, but you don't have any time. So he creates these imaginary numbers to describe this timeless. I just want to put that out.
Well,
okay?
let me tell you about imaginary number before I go back to this. Imaginary number is used in electrical engineering.
Okay.
It's just a simple, the square root of -1.
Okay.
And you can put that in an equation. You call it I. And you put that in your electrical engineering equation. And if you're trying to measure the resistance, we call it impedance, but the resistance of an induction coil, you send current to it at first in an induction coil, and it will give you a resistance.
All right.
And if you keep it there for a long time, a constant DC current, its resistance will go to nothing.
Okay.
Now, if you take away the electrical power supply, all of a sudden, instead of it being resistance, it's going to supply power back at you, a negative power.
Okay.
How do you represent that? You represent that by I. And
Which
so,
would be the square root of -1.
the square root of -1. So you've got an equation now that will predict how that induction coil resistance or impedance, they call it, is.
Okay.
And so it's
so it's describing that mathematically.
Right. It's a negative resistance. A negative
okay,
resistance.
a negative resistance would be a force.
Right. It comes back.
It's coming back as a force, but it's not really there.
Yeah, it's a power back at you.
Power
so that's
back
how they're using imaginary numbers.
Okay,
right?
so that's what an imaginary number is. All right. So that helps a little bit. Now, does it seem strange to you to think that there is space but no time? I don't know how to put that into context, because I can't imagine there being space without being the movement of time, you know?
Right.
And I think we have to have that in order for the badminton to look, in order for the universe to look like a badminton net. He says, now, before you tell me your example, he says here, all one can do is find which mathematical models, this is Hawking, describe the universe we live in. It turns out that a mathematical model involving imaginary time predicts not only effects we have already observed, but also effects we have not been able to measure yet, nevertheless believe in for other reasons, quote unquote.
Right.
So what is real and what is imaginary is the distinction just put in our minds. That's Stephen Hawking, and he talked about that in the recent movie about his life. So tell me your example now.
Right.
Give me your example.
This is what these guys are doing.
All right.
Let's go to the Trinity site in New Mexico, where the very first world's first atomic bomb was exploded.
Okay.
It was a 15-kiloton nuclear explosion. When it went off, it turned some of the sand underneath of it into glass.
Okay.
If you were to take precise measurements, you can probably, with that glass, you can probably predict how the explosion happened.
Okay.
But what these guys are
because
doing,
of the residue left over.
yeah, because of the
you're making predictions based on what you see.
On what you see.
The result.
What these guys are doing is they're looking at the glass, looking at that glass, and they're making a prediction on what was the man's name who ran the crane to put the bomb up on top of the stand. All right, does that make sense?
Yeah. So what you're doing is you're trying to extrapolate, it sounds to me like, from proof that you do have, the sand, a fact that is beyond what you can get at with numbers and proof.
I mean, they're taking precise measurements of the cosmological background.
Right.
But what in the world, and that, that's close to the Big Bang, but it's nowhere near what happened at the Big Bang. And it certainly is not going to tell you what happened before the Big Bang, right?
So you're moving backwards on this cone, and the question is, how far can you really go back with that cosmic background radiation? I mean, really, Doug, we're any of us, whether it's Stephen Hawking, I know he holds Newton's chair, all right, at Oxford, and I know Krauss is a professor of physics, and whatever, and we have our accolades, but the point of it is, it doesn't matter if it's me, you, or Krauss, or even Hawking. You still cannot do the impossible. I mean, you're not able to make predictions about something you can't see.
You're taking precise measurements of glass and sand. All right.
So he's basically, what we're saying is, he has faith. in his theory.
That's what he's got.
He has faith.
All right.
All right, so we're going to have to wrap it up. So this has been a good show, though. I think we've made some progress.
So this is God Talk Improv, where we mix up science and faith in 15 minutes. Thank you.
Please visit our website at godtalk.com. Our audio files can be found on iTunes, SoundCloud, and many other podcast platforms. You can find all of our God Talk videos by searching Dr. Andy and Doug on YouTube. Please visit our Facebook page at www.facebook.com/Dr. Andy and Doug. Thank you for listening.